Okay, kids, so we're going to talk about product rule, quotient rule, and higher order derivatives. And we learned last time how to take the derivatives using the power rule. But when we have two functions that are being multiplied or divided, we have to learn these new rules. We're also going to talk about trig functions and higher order derivatives. So first, the product rule. The product rule states that when we want the derivative of two functions that are being multiplied together, we take the derivative of the second times the first function plus the second function times the derivative of the first. So there's a little rhyme that goes with this. If the product rule must be done, it's 1 prime 2 plus 2 prime 1. Okay, so let's look at what that looks like. Here are two different functions. Okay, now we could multiply this out, and that is really what I would rather do if I could do the power rule, but we got to learn how to do the product rule, so we're going to start with one that's not too bad. So understand, we could multiply it out and do the power rule. Instead, we're going to do the product rule. So h prime of x equals the first one, 1 prime 2. So we're going to start off with the first function, which is just 3x minus 2x squared. Don't change it. 1 prime 2. So we're going to multiply by the derivative of this term. So I'm going to have 0 plus 4x, or just 4. Everybody okay with that, hopefully? Then I'm going to do plus the second function, 5 plus 4x, times the derivative of the first. So I do each term individually. 3 minus 4x. Okay, so I have some cleaning up to do, and I'm going to distribute here. So my derivative, here's the 1 prime 2, 2 prime 1. I'm going to multiply that out. I have 12x minus 8x squared, plus, I had to distribute here, FOIL it if you like that, 15 minus 20 plus 12 is minus 8x, and then minus 16x squared. And then I'm looking for any like terms that I have. So at the end, my rule is negative 16x squared minus 8x squared, negative 24x squared. 12x minus 8x is plus 4x, and then plus 15. All right. Again, if we would have gone back to this original function and looked at if we would have distributed it, we could have had 15x minus 10x squared, 15x minus 10x squared plus 12x squared minus 8x cubed. These combine. So if I had 15x plus 2x squared minus 8x cubed, and I did just the power rule, here's my 15. This is going to be 4x. This is going to be negative 24x squared. You can see it right there, right? Easier to do this, but right now we're trying to learn how to do the power rule when it's more complicated. So there we go. Ta-da. All right, quotient rule. The quotient rule is a little bit more complicated in that we have a high part and a low part. This is like the numerator, the denominator. So the quotient rule is low d high less high d low all over the denominator squared. Okay, so because it's a difference, it's really important that we get the order of these right, and we have to be careful that we're not switching the terms, right? So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the denominator squared. So let's look at a quotient rule problem. Okay, so y prime is going to be the bottom, x squared plus 1, times the derivative of the top, low d high, which is just 5, less high, hi, how's it going? D low to x all over the denominator squared. Now I'm going to leave it just like this, and I'm not going to simplify that if I can help it. I want to write that a little bit nicer. Because I don't have, that creates more x's, right? The numerator I have to simplify. So, all right. So we're going to distribute and try to simplify the numerator. 5x squared plus 5. And then when I get this minus, I got to make sure the minus gets to each term. So I'm going to have minus 10x squared. And then 2 times minus 2 times negative here is going to be plus 4x all over x squared plus 1 squared. And when I simplify that again, y prime equals, I'm going to combine like terms. So I have negative 5x squared plus 4x plus 5 all over x squared plus 1 squared. Now you could think about factoring here, but I don't think anything's going to factor. We don't have a common factor of 5. It's going to be tough to get a 5 to add to 4 when there's this leading coefficient over here, so we can't do that. So we can stop. So anyway, low, the denominator, d high, the numerator, less high, d low, all over the denominator squared, and just leave it. There's the quotient rule. Okay, so some more derivatives of trig functions. We can actually prove these using the quotient rule because these all have fractions in them, right? If I look at tangent, for example, tangent is sine x over cosine x. And if I do the power rule, or sorry, the quotient rule for this, I have low d high less high d low all over the denominator squared. And when I simplify this, I have cosine squared plus sine squared x. And at this point, you hear the songs of angels because sine squared plus cosine squared is heaven. This is where we want to simplify and get that Pythagorean 1 over cosine squared x. And 1 over cosine is also secant. So this is how we got secant squared x, for example. All right, so if we have x minus tangent of x, we're going to do these as separate things. The derivative of x is 1. The derivative of tangent is secant squared. We just saw that. So we're taking the derivative of each one separately. If I have x times secant x, here I have to do the product rule. So it's 1 prime 2. And if we go back to our table here, secant x is secant tangent. So 1 prime 2 plus 2 prime 1. And then we're going to distribute what we can, try to simplify things. This is all one term, really. There's nothing to distribute. I could factor out a secant from both things. I don't know if that's better. Have 1 less x to have to plug into, so maybe it's better. So summary table below shows a work in simplified form of derivatives after differentiating. So we go through and we take the derivative, step 1, but then we have to combine like terms, multiply out, all that stuff. So we can see, note the 2 characteristics of a simplified form are the absence of negative exponents. So we don't have any more negative exponents, and the combining the like terms. And truly, kids, we're trying to get it to be as few x's as possible. Okay, higher order derivatives. Higher order derivatives just means I'm going to take the derivative of a derivative, and maybe more than once. So if we have our position function, going back to our physics applications, we can get velocity by taking the derivative of the position function. Okay, velocity is the derivative of position. You should have that in your notes if you don't already. Acceleration is the derivative of velocity. which is the derivative of position twice. Second derivative. That's two primes there. We call that the second derivative. So the function a of t is the second derivative of s of t and is denoted by s double prime of t. The second derivative is an example of higher order derivative. You can define derivatives of any positive integer order. For example, third derivative is the derivative of the second derivative. After we get past three primes, it becomes tedious and we just start putting numbers up there as if they were exponents. We put them in parentheses so you know it's not an exponent. A little easier with our notation here. So you'll see the second derivative, third derivative, fourth derivative in terms of change in y over change in x. Also helps with your physics applications to think about the units. If we're doing velocity, we're in meters per second, for example. If we're doing acceleration, we're in meters per second squared or meters per second. So also something to think about there. All right. Because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fell at the same rate on the moon. Position function for each of these falling objects is given here, right? Different gravitational constants, so we have this new function where S of t is the height in meters and t is the time in seconds. What is the ratio of Earth's gravitational force to the moon's? So to find the acceleration, we're going to differentiate the position function twice. So here's our position function, and we want to find the acceleration. So the first derivative is velocity. When we take the first derivative, we can get this. There's our velocity function. When we take the derivative of the derivative, notice we get a constant acceleration. This acceleration function doesn't have any variables, so it's constant. So the acceleration is always negative 1.62. Our gravitational constant on Earth for meters per second was 9.8. Gravitational constant for the moon is 1.62 we just found. And there's our ratio, which simplifies to 6. So the Earth has 6 times more gravity. All right, that's it for the notes, kids. You have a WebAssign assignment to work on for the rest of the block. And you may also discuss the homework questions from the power rule homework that is still due, but it's due at the end of the block. All right, have a great day.